Right? Does this work?
Yeah.
Yeah. Okay. All right. So hi everyone. So I would like to thank the organizers for this nice workshop and for the invitation to be here. So I will be talking about non-linearities in turbulence and some statistical analysis that we've been doing with this. So the framework I'm going to present this is related to input, output, or resolvent analysis. So I will go through this briefly. So if you just start from Navier-Stokes and you go to the frequency domain, there are some things that you gain, but you do get a complication over here. So what I've done is that the terms that are related to the mean flow, they are zero frequency, and I'm putting them on the left-hand side. And everything else from the convective term that is non-zero frequency, I'm leaving here at this right-hand side. So when you look at this part, you end up with the linearized Navier-Stokes operator, linearized around the mean flow. But you're left here with the generalized Reynolds stresses. So it's like the Reynolds stresses that we're used to, but they're at non-zero frequency. So this is good because we know a lot about this linearized system, but there's this convolution here that makes things more complicated. So the available options are, we can just forget about them. So that's been used a lot, especially for free shear flows like jets and mixing layers. Or we can try to do something about this. One thing is to try to do some closure. So somehow you try to relate these to your mean flow to have a closed form system. That has been tried since the 70s, but got renewed interest in recent years. And the other thing that you can do is that, fine, I don't know much about these, so I'm going to treat them as a forcing term that will somehow drive the system. And that also gained a lot of interest in recent years. So you end up with analysis of a linear operator that you can cast now in input-output form. The basic idea is that this term here becomes a forcing term, right? And we treat it as an external forcing, and we try to understand how this forcing will drive a response of your operator. And so if you move this to the right-hand side, you end up with the resolvent that can be analyzed to try to get what is the optimal forcing and the most amplified flow response here written as Q, right? So the underlying idea is that whatever is the optimal response, the most amplified response through the resolvent is a likely structure that will emerge in a general turbulent flow. So the way this is done, briefly, you take a singular value decomposition of this operator. Here in matrix form, you write the resolvent as singular vectors, left, right, and singular value sigma, in such a way that your outputs and your inputs will be rated by this expression. So once you write the outputs and the response basis U and the inputs and the forcing basis V, they're related one by one through these gains, sigma. So if you force with one of these elements, then you get the other amplified by sigma. And of course, the largest singular value will give you the optimal forcing and the most amplified or optimal flow responses. Then the other ones are the suboptimals. But now we would like to compare this to turbulence data. So how can you do that? Because things are not harmonic. We're in the frequency domain, but the system is stochastic. So the way to do this is to work with covariances or cross-spectral densities. So if you write things in the frequency domain, then you can, this quantity here is well defined, the expected value of a given flow quantity. So, so this will become a matrix once you discretize. The diagonal will be just the power spectrum as we're used to. There are, of course, off-diagonal terms, which are cross-spectral densities between different positions of your flow or different variables, right? You can do this relatively well these days, especially if you have numerical data. You need to store a lot of data, but you can also get away with experimental data, provided that you have measurements that are space and time resolved. So this matrix here is interesting because it can be written in terms of the resolvent. So since you can write your output as a function of your forcing, then the resolvent is deterministic. You can move it out of this expression such that you can get the statistics of your flow as a function of the statistics of your nonlinear terms, which are here written as F, the forcing. And if I now take a step further and do strong simplification, if I say that my forcing is white noise in space, so for a given frequency, I'm saying that my amplitude is uniform, equal to 1 everywhere, and have 0 coherence in my forcing between neighboring positions. That's very strong, but the result is very nice because this becomes the identity matrix, and it just vanishes from my expression. So I end up with my flow response. We'll have statistics that are given precisely by your output modes in such a way that if I take eigenvalues and eigenfunctions of this matrix, I will end up with POD modes in the frequency domain, or spectral POD modes. And on the right, I end up with my resolvent modes. So there would be a one-by-one correspondence between your data, modes from your data, and modes from your linear operator, right? Well, it's a strong assumption because we know that this cannot be true. Any quantity any physical quantity needs to have a finite coherence length, cannot be completely incoherent. So you expect some coherence of the forcing. This cannot be true by this. And we also expect spatial variations of the amplitude. We know that the nonlinear terms should drop to 0 on the wall. They should be stronger in some regions and weaker at others. So we should be careful with this. But this remains something interesting to look at because when you rewrite this, now I'm just grouping these middle terms here. I'm not assuming that this is white noise. You can also see your flow statistics as a sum, as weighted by your forcing cross spectral density, now written here in V space, in the input space. And especially if there is a large gain separation, if there are singular values, the first one is much larger than the 2, you could end up in a situation where, despite this not being white noise, you still end up with leading SPOD mode that is close to your first resolvent mode, right? So that's the underlying idea of how we apply this input-output analysis to a turbulent flow, right? So regarding what happens in wall turbulence, this has been mapped out by a number of people. This is by Huang and Kosu, who are here. So this is for turbulent channel flow. And this plot here is showing a cross-section of turbulent channel flow with the resolvent modes. The forcing is given here by the arrows, and you get the forcing in the shape of a streamwise vortex. And the response here is shown by the lines. With the contours, you have a streak. So these correspond to this near wall structure that you can relate to the lift-up mechanism. So you have these rows here advecting fluid and creating these strong streamwise streaks. So this has been out for some time now. What happens if you compare that to turbulence data? So what you can do is take some channel flow data and apply SPOD to that. So let's see how it looks like. So this is for turbulent channel flow. We'll focus on this case in this talk here. The friction Reynolds number is 550. And so it's relatively easy to get DNS data at this condition these days, right? So on the left, you have your SPOD modes, first mode and the second mode, so taken from turbulence data. On the right, you have your first and second resolvent modes. So there are two ways to see this. You could think that, if when you look at the overall features, they're nicely reproduced. So you have the streaks, you have the rows, they look more, and they have this staggered arrangement that matches what you would expect. So the overall features here in the leading mode are relatively well represented by your leading resolvent modes. The second mode, both in SPOD and resolvent, has this double shape here, 2 streaks and 2 rows, representing variations of this pattern. But when you look at the fine details, they are different, right? So these are much more extended in your data than in your input-output analysis. So which now we can attribute to the forcing. So it's not white noise, so you don't expect them to be identical, right? So what can you do about it? There are some ways about it. So one thing is to try to use an eddy viscosity. So I think Carl Koss is probably going to discuss this in more detail tomorrow. So this would do the trick here because it would spread a bit more these structures and they would look closer to what you have in the data, right? I will talk about something slightly different that we've been trying to do these years, which is actually taking the forcing data from a simulation. You just go to your DNS, you compute these nonlinear terms, and you do, this becomes F taken from the data, and you get the covariance of this. Because, well, if you know your forcing exactly, then you will get the response exactly. So there's no simplification in this procedure. So it's quite data intensive, but you can probe this relationship in some detail as it comes from your data, right? So we did this in a couple of papers. First one is for minimal QET flow. And the channels that I'm going to show here, they're coming from the second paper. And so first thing that we needed to do is to check that everything is correct. So what we did was, okay, I'm taking here just the power spectra, U in black, V in red, and W in blue. So the lines are coming just from the DNS, and the symbols are coming from this expression here. So everything is consistent. We can recover the DNS statistics up to like several orders of magnitude, up to numerical accuracy. So of course, the relationship holds. The signal processing seems okay. Now we can try to explore this forcing to see what it looks like, what it does, and how it generates this response. So the first thing to notice is that the forcing is quite coherent, right? And how can we do this? What we did was, instead of looking at this full forcing statistics, we just took its leading mode. So if I do a rank 1 approximation of this matrix here, and I plug that into this expression, I recover the dashed lines. So of course, it's only a subset, it's below the full thing, but it's not far. So the most of the streaks are reconstructed just by taking one mode of your nonlinear forcing, right? And the same thing for the other fluctuations. So this is for typical near wall structures. So span-wise spacing of 100 viscous units. When you look at larger scale structures here, now they are spanning the entire channel. This is even this is even clearer. So again, with just the leading forcing mode coming from your data, you recover almost all your turbulence statistics, right? So the other thing is that that we realize from the data. So unlike what you do in resolvent analysis, input-output analysis, you're looking for like optimal mechanisms. So what is the forcing that drives the optimal response, the most amplified response? What we realize by looking at the data is that the forcing is really suboptimal. And the way to understand this is by breaking into components. So P here is my forcing statistics, S is my response statistics. And well, forcing has 3 components, so you can break this matrix in like X component, Y component, Z component, and there will be cross components because this is a covariance. So when you look at individual components, they are up here. So this is for near wall structures. This is for large scale structures. The individual components are up here. They're much larger than what you have in the full data in your DNS. What is happening is that when you add these components with the cross components, 1, 2, 1, 3, 2, 3, you're back in this middle line here, which is the DNS. So there's a lot of cancellation taking place between these individual blocks, right? So the forcing is not doing, is not taking a lot of advantage of an optimal mechanism. It's quite suboptimal, right? And well, just a sort of different slide here. This is not for the channel. Again, now I'm doing this for transition. So this is a transitional boundary layer with free stream turbulence of 3%. So this is something we're working on right now that kind of joins what George presented and also Mihailo in the first day. The same kind of formalism also applies for transitional flows. Now, here with this flat plate boundary layer, what's happening is that there's some free stream turbulence outside that is exciting a growing streak, as you see over here. And again, you can play the same game here. It's a bit different because there are upstream conditions and there's nonlinear effects here in your domain. But if you do everything right, construct your resolvent, then you can reconstruct whatever response you have in your data to pretty good accuracy. So that allows you to split between different mechanisms and to try to understand who does what in these scenarios where it's transition, but it's a complex disturbance environment. Okay, now back to the channel. Let's do something else here. So this is something that you can also do with your data. If you now have all your outputs and inputs written like this, so these are individual realizations of each thing. And so they are all mapped from one to another via the resolvent operator. There's something else that you can do here is to try to look for the forcing that will correspond to a given SPOD mode in your response, right? So if you take the same technique that you do to get your SPOD modes of the velocity fluctuations, and if you apply the same reconstruction to the forcing matrix written up here, you end up with a forcing mode that generates the response SPOD mode by construction. So this is a form of extended POD or SPOD, but is related to the resolvents. So that can help you identify the bit of the forcing that's related to a response of interest. So let's see how this looks like. So what we did here was to identify something related to wall shear. We took the span-wise shear on the wall. And so what we did was we looked for coherent structures giving a signature there. So these are results for 3 wavelengths with fixed aspect ratio. And what you see from right to left is the wavelength going from small to large. And as everything has been rescaled to try to enhance the similarity, you're getting the same pattern over and over with these streaks and the rolls. It's just that the plot on the left is much larger than the one on the right. That's what you have, and that's what many people have identified in the past. What we realized was then when we look at the forcing that is connected to these structures, you also have something that is self-similar. So you get the same pattern, it's just scale up and down, becomes larger or smaller depending on the size of the structure that you're considering. So that's a bit useful. It would be quite disappointing if if it were completely different, then we would have a tough modeling test. The fact that we have something that is similar, that is good, because in a sense, we could embed that structure into linearized models to improve them. And at the other side, other thing we can do is to explore mechanisms that give rise to this. The pattern that we see is a bit complicated. The forcing is not divergence free. It's different from what you have in the velocity. It's like the nonlinear term doesn't need to be divergence free. But it has a clear structure. It appears over and over when you look at wall turbulence data. And now this is a bit of a spoiler of Aeronáutica, which is coming just after mine. I would just highlight that there's another useful application of this, which is to build linear estimators. If you have access to your forcing statistics, you can write an estimator. So let's say you have some sensors Y, and you want to estimate your entire velocity field tilde written here. So the optimal linear estimator can nonetheless include statistics from non-linearity. So here they are appearing here as FFH. So I can use that to build my linear estimator. So it takes into account at least part of the non-linearity, right? And there is sensor noise. So this is an expression that we also apply to the same case. So here are snapshots moving from close to the wall to further from the wall. The first row is what you have in the DNS. And what you can estimate from your wall measurements is shown here on the second row. So if it's PFF equals true, meaning that I'm taking into account the bulk of my statistics. And the near wall fluctuations can be almost entirely recovered. As I'm moving further from the wall, I lose some of the finer detail, but you can get the larger scale structures here. They're relatively well captured by your estimator. But if you don't have that, then you lose it. So if you just assume you have white noise, you can still recover things that are very close to the wall. But as you move further from the wall, now your predictions are very far off. So that illustrates that you should somehow take these into account to get something meaningful out of these linear estimators. So that closes the talk. So I guess the main point here is, I mean, input output is very useful. You have some analysis of your of a linear operator that helps you identify mechanisms and everything. But these days, we can get detailed data on whatever is driving this linearized operator from experiments or simulations. So it's useful to look at these a bit in more detail to try to understand how this connection is made, right? And the data is available. So if someone is interested in looking at that, I will be glad to share. So thank you.
Okay, thank you. We have time for a number of questions.
Yes, in this true forcing that you're putting there, you're not putting the pressure.
No.
Why not?
Well, the pressure comes as a response.
Well, but the slow pressure should be there. I mean, the fast pressure is in your when you're in your resolvent, but the slow pressure. I mean, that's why your forcing is not solenoidal.
So I just wrote Navier-Stokes here, but I also have continuity, right? So what I have is I drive the momentum equations with the nonlinear terms, and I get everything, velocity and pressure.
But the slow pressure is a nonlinear term.
Well, it depends on the linearization that is done. So we're linearizing around the mean flow, and then the pressure, as it appears here, is a linear term.
Well, I'm just wondering whether part of the reason why your forcing looks so suboptimal is because you are missing the slow pressure. When you are putting the slow pressure in the wrong place.
Yeah, it could be. It could be. Well, I mean, let me phrase it this way. You have some freedom here in your linearization, so you can linearize around various things and move some things to the input or leave them in the output. The way I'm doing now is that the pressure is indeed inside the operator is computed as a response. I guess what you're trying to say is somehow I leave that thing out, I would end up with like a solenoidal forcing. Yeah.
I mean, that's what the pressure does.
Yeah, maybe that could simplify the test. That's a good idea. Yeah.
That does everything. Everything else is just being. Yeah, it's only the solenoidal part of the forcing that has any effect. The other thing is just getting into the pressure. So it doesn't matter, I think, if you do it or not.
Not really, because I mean, you know I mean, the forcing has components in other wave numbers. The slow pressure is a fully nonlinear term. I mean, you just take the sinusoidal part of the forcing and then put that pressure, you put it into the linear operator, you are mixing wave numbers, basically. That part is not linear. You will not, I mean, it doesn't scale linearly. You multiply the velocity by 2 and the pressure scales by 4.
I think it's the same as if you start forcing the Navier-Stokes, full Navier-Stokes nonlinear equation with something non-solenoidal. Only the solenoidal part would give you velocity, and the non-solenoidal part would just add to the pressure, but you will never see any response in the flow from that. And that's what happens here.
I think we highlight this.
It is indeed nice talk, and it is indeed interesting observation about the forcing being suboptimal. But what is optimal, what is not, depends on the measure of what is maximized when you optimize. So basically, you take L2 norm of the response and seek input which maximizes that response. Why that norm? It might be that the correct way of doing this is to use a different norm, and attention could be paid to the question, what actually should be optimized in order for the structures to really represent what we observe in turbulence. So that is just a suggestion. But well, that was explored before, and it looks like energy norm is not always the right one. It depends on what you actually are going to look after. If it is the forcing, then probably it should be something else to look at, not the energy. Sorry, it was not a question.
Yeah, I agree. The way it's usually done when you're doing resolvent analysis is that you need two energy norms, one for the output, another for the inputs, and then you have a gain, right? They're different.
You can have any two norms.
That's true. That's true. So
then think what is the right one.
yeah, that's an interesting question, I guess. That's an interesting comment, though. Yeah.
Hey, Andre, very nice talk. So you provided an overview of the approach in the frequency domain. And as you argued, if you compute statistics of forcing power spectrum or forcing, you can compute now statistics of velocity. But there is an alternative approach to the problem that utilizes time domain formulation, where essentially you can use statistics of velocity fluctuations that is publicly available, and even partially available statistics, and formulate an inverse problem to identify power spectrum of the forcing that gives you statistics that are consistent with data that is generated in DNS. And you provided pretty generous literature overview. These results have been out for 5 years already, published in JFM, and for whatever reason you decided to not mention them. Do you feel that they are not related to this? Can you compare them?
It's quite related, and I should probably have cited that. It's fair enough. You can do that in the time domain. You end up with sort of Lyapunov type equation, and of course there's the driving term, which will include some statistics. I guess the thing we wanted to do here is we wanted to extract this from the data, right? So we really wanted to carry this out by looking at the full nonlinear term. The advantage of doing this on the frequency domain was that we could look at the individual frequencies separately. If we would do that in the time domain, I would need to include a time delay, and for some of my results, they would be more, I mean, at least for me, they would be more complicated.
See, at the end of the day, actually, if you take a look at the formulation that is provided in the paper that I'm mentioning, you can go back to the frequency domain and do these things. But there is a fundamental difference in the approach. You rely on data-heavy technique here, where you need to compute additional things from DNS, whereas in this approach that I mentioned, Color of Turbulence paper, publicly available data from Javier's website was utilized, and you estimate statistics of the forcing. So at least conceptually, these things are related. So for full disclosure, they somehow deserve to be mentioned in the mix of available approaches to this problem.
Yeah, I hope that in our papers we definitely cite that one. I think so, but I will need to check. So the only remark is that I think you're completely right. The only thing is that what you get from your output data is whatever's observable from your output. So if you're dealing just with velocity data, I mean, joining the previous discussion, you will get the forcing, but the forcing that is observable from whatever velocity information you used in the first place. So if you don't add the pressure, you might lose at least part of this forcing. So here, no, what I'm saying is that, I mean, the forcing that you get, that you can use from the output, is whatever can be observed from this output. So if you use the full output, of course, you can observe everything. But if you're using partial data, you will observe whatever part of the input that will affect your output.
Okay, in the interest of lunch, we're going to move on to the next speaker in the session. So thanks, Andre.
Thank you.
Okay, while the next speaker is getting set up, I'll go ahead and introduce